So for this video on heteroskedasticity, recall that what heteroskedasticity means is that it violates the single regression or multiple regression assumption of the variance not being constant. So visually, we can see that in the first graph, we have a constant variance as because our x variable increases, our variance relatively stays constant in contrast to the heteroscedastic model, whereas our x increases, our variance actually increases. So it does not stay constant. And because this violates the MR/SR assumption, it has consequences of being heteroscedastic, which is that it's still linear and unbiased, but it's not a best linear unbiased estimator. And so what that essentially means is that it no longer produces the literal lowest sum of squared errors among all the possibilities of our estimators. And that's a problem because, when we first went into linear regression, we learned that the ideal model is one that minimizes the sum of squared errors. But because of heteroskedasticity, our fitted model doesn't do that. Even though in this function it may look like it, some of the fitted values, it may go across like this or maybe below the line. And so the SSE can be lower if we correct for it. We're not going to learn how to correct for it in here, probably the next video where I start a new series on multivariable regression, but we will learn how to detect it. But anyhow, because the unbiased estimators, or because the estimators are no longer blue, that means our confidence interval and hypothesis will be incorrect. But our LS estimators we can still use, so like our beta 2, beta 3, beta 4 will be went over in our past videos. Those we can still kind of analyze with, slope and elasticity and all those sorts of stuff. But when we're doing test hypothesis, we should first correct for heteroskedasticity first. And so how do we detect that is we have an informal method and a formal method. We usually want to use the informal method first because that's faster. And that usually involves just the visual inspection of a residual plot. All right. So primarily there are two methods of detecting heteroskedasticity. First one is what we call the BP test or the white test. And so these 5 steps are pretty general. They don't include all of the mathematical processes, but we'll regress the function as usual. We'll collect the residuals or the errors. We will square the errors, and then we will actually regress the errors. So like, if you can see here, we'll square the errors. We'll first find the regression function. We'll square the errors, and then we'll regress that in terms of the other explanatory variables. And so if our chi-squared statistic is high, based on right here, sample size times the r squared, if that's high compared to the critical value, then our null is rejected, and so we conclude that we have heteroskedasticity. I am not sure why I didn't write it here, but similar to the null, whenever we're testing for heteroskedasticity or something, the null will always say it doesn't have it, and then our alternative say is it does have heteroskedasticity. So if our chi-squared statistic is high, then or if it's higher than the critical value, we will reject the null hypothesis, and we conclude that there is heteroskedasticity. And so that's one method. The other common method is what we call the Goldfeld quant test. Short for, we can also call it the GQ test. So this uses a pretty different method. What it will do is, if we see the heteroskedastic data here, we will regress this part into two sample groups. One part where the variance is greater, and one part where the variance is smaller. The specifics into how we divide these groups, I'm not going to get into it. I'm not entirely sure how, but we assume that it won't always be effective, but visually we can kind of see that this is effective because the left part and the right part of the group, their variance is clearly not the same. But the whole point of it is to see if they're the same or not. And so there will be two regressions formed here and here, and then we'll calculate the F statistic for both of them. And so when we calculate the F statistic, our higher F statistic will always be in the numerator. Our lower will always be in the denominator. And so if the F statistic is high, also known, we can also interpret that as if our variance of one sample group is significantly greater than the other, then that means there is heteroskedasticity because we want a relatively low F statistic if we're looking for a homoskedastic data. And so if this value F is high, that usually means we want to reject the null, and the null saying that the two groups are have the same variance. And so when we reject the null, our alternative is that the two sample groups have different variances, and so we'll reject the null, saying that and conclude that there is heteroskedasticity. And so those are the two most common methods. There are other methods like the FGLS estimator. That's where we also make the function like blue, where the white test doesn't necessarily make the function blue, but it will make the function heteroskedastic. But I'm not going to go over that. Again, if you want to go over all of those sorts of stuff, you can, but this is just a brief concept on heteroskedasticity. So that's pretty much going to be it for my all my concepts and topics on my linear regression. I will go over more specific concepts of heteroskedasticity. Similar to heteroskedasticity, I'll go over autocorrelation in the next playlist or set of videos where I'll be covering over multivariate regression. But for the simple linear regression, not simple, but just linear regression topics videos, I will end it here.